So is this being recorded? No. Pratik, is this being? I don't know. Okay, I think it's recorded. Yes. So anyway, I'm pleased to introduce all of you to Anagha Vasudevan, who's the speaker for today. So Anagha first came to us during one of the open days of IISc, which is an annual event. I think it was in 2010 or 2009 when we were still in the old building. So she's from Bangalore and she was a student, I guess, at the Valley School at that time. And then she would come and meet us because of her undying love for physics. And then after school, she went to St. Stephen's College in Delhi, and then went on to the RWTH in Aachen in Germany for her master's, where she's written a nice paper with Les Gouge and others on cosmology. And then she moved to Niels Bohr Institute in Copenhagen, where she's about to finish her PhD and soon become Dr. Vasudevan, I guess. So she has published a paper on effective field theories with Trott and others. And today she's going to talk about a part of her thesis work, which is being done under the supervision of Bohr. And she's going to tell us about effective approaches to gravity. So over to you. And Pratik, I think, will take over and he will manage the questions, the questionnaire and all these things. So I'm here, I'm not going anywhere, but you can ask, I guess he can decide when people will ask questions, whether during the course of the talk, towards the end, as you all see fit. Okay, so over to you.
Great. Yeah. Thanks a lot. So everybody, just let me know if you can't see me or hear me or something like that. If there's some issue there, just stop me in the middle of it. So hi, everyone. I'm Anagha, as Anand sir introduced me. And first of all, I wanted to say thanks to everybody for attending my talk. And thanks Anand sir as well for setting this up and guiding me through all these years. And also a final thanks to a few of my friends and family who were nice enough to join today. So like we said, I'm currently at the end stages of my PhD at the Niels Bohr Institute in Copenhagen. And the topic of my PhD is effective field theories, I would say, in general. So I started off with working more on standard model effective field theory, which is more like a collider approach, which helps you make LHC predictions and stuff. So that's kind of the domain where effective field theories was mostly used. But over the course of my PhD, I've been learning more about, instead of just using it on particle physics, what about applying it to things like gravity? And I hope you'll be able to appreciate at the end of this talk that the idea of effective field theory is actually pretty universal and will be, we can use it for a lot of different things, basically. So, it's a bit difficult to scroll, but I hope you can see the cursor as well. But when I came to IISc last week, I had told Anand sir and some of the students who I met there that I want to talk about gravity. And I was met with a certain degree of confusion because people were like, is that cosmology? Is that astronomy? Is that particle physics? So to begin with, I thought I should try to explain that to you, what this talk is about. So the story started in 2015. And the plot here is hopefully familiar to a lot of you. So it's from the LIGO collaboration. And it's the first example of us observing two black holes basically merging into each other and becoming one larger black hole. And this was an event that was recorded in September of 2015. And it's basically like started an entire new field, I would say. This was a field that existed in the past, but we'll see that it's had a huge revival in the last couple of years just because of this. So in the plot that you see here, I don't want to say too much about it because I'm sure everybody knows, but we essentially see what happens when two black holes collide. If you just want to naively just look at this frequency that's changing over time, what we're watching is two black holes coming closer and closer together, and the gravitational radiation between them increases until we reach some kind of peak point where they merge. And it's a pretty catastrophic event. So that's why we were able to observe it all the way over here. And then there's the more peaceful part that comes afterwards where they've kind of merged into a single black hole. And basically, you can see on the different plots like how they observe this at two different laboratories in the US. And this observation has basically kickstarted the whole field of gravitational astronomy, something that people have been excited about, I think, since Einstein predicted something like this back in the early 20th century. So, I mean, gravitational wave astronomy itself is extremely interesting because it's going to, like, if you're a cosmologist, it's really interesting because you can go all the way back in time and observe the gravitational waves from the early universe and so on, and it offers a chance to like look at something we've never seen before. But on the other hand, like, there are also astronomers who are extremely interested in this field because you can learn more about how these black holes merge and their structure and different properties of the actual black hole itself. But as for me, and I think most of the audience here were into theoretical physics and perhaps the theory of everything and so on, I think there's a great excitement in being able to study a complete theory of gravity, because this gravitational radiation will allow us to study gravity in many different regimes. And I will be elaborating on this shortly. And as for me, since I'm not an experimental physicist, when I look at this plot, my interest is in seeing how I could describe this using the methods that I know. And the methods that I know are those of effective field theories and to some degree scattering amplitudes. And this talk is actually going to be about how these three fields work together and sync so well. And we actually are getting closer to having more and more precise analytic results. And this is extremely important right now, given that LIGO has just about reached its peak sensitivity. And soon there are plans to expand LIGO as well to countries all over the Northern Hemisphere, the very least. And hopefully they're going to come to India as well in the form of Indigo. So I think there's going to be a lot of data. And already since 2015, there have been a lot of observations of different kinds of these mergers of large massive bodies. So it's not just black holes like in this plot. They've also observed neutron star mergers and neutron star black hole mergers and stuff. And this is currently a very exciting field for anybody working on anything, I would say. So with that in mind, I thought I would give you a brief outline. So I'm going to be talking about a lot of different things today. And so for that reason, I won't be able to go that much in depth, but then you can ask me the questions. And if I don't know the answer, I know where you can find the answer. So we can do it that way. So I'm going to start by explaining this two-body problem in general relativity a bit more, because there are different aspects to this problem. And of course, if you're working on effective field theory and amplitudes and so on, you know already that there's a range of scales where you can work on this problem. And I'm going to tell you more about what those ranges are, what those limits are, and so on. And then I'm going to go further to explain to you what I have been calculating. So to begin with, there's an effective field theory formalism that's based on just the standard, very bare-boned idea of effective field theory and how to construct one and so on. And I'm going to explain a bit of how that formalism itself works. And that is going to lead me to show you some results that I recalculated, that my supervisor previously calculated for corrections to both the Schwarzschild and Kerr metrics for black holes that are with spin and with spin half and so on. And I will also be telling you why this calculation is so hard. I think you will get a slight appreciation for that. And we've been trying to work on an alternate method in order to solve this in an easier way. So that's what we're currently working on. And I will explain to you the struggles of that as well. And I wanted to overview some of the other methods, but it doesn't look like I have much time to do that. So for that reason, I think I should just mention it very briefly and earlier. And I'm going to focus more on showing you some of the results that people have obtained of late within this theory. And finally, since so many people at the Institute seemed interested in amplitude methods and stuff, I thought that I would discuss a bit like why people have a huge interest these days in extending these gravity effective field theories to unitarity-based methods. And yeah, to some degree where we are right now on that regard. So yeah, just let me know if you have any questions and I can send you sources about anything more. So we're seeing a slightly different version of the first plot that I showed you of the first merger of a gravitational hole. Two black holes. And like I explained, there are 3 stages in this whole thing. They're called the in-spiral, the merger, and the ring down. So the in-spiral is actually the longest part of the whole signal. So you can see it actually covers most of the page, and it's the part of this whole merger where the black holes are rotating closer and closer to each other. And as you can see in the little plot below, you can see that their relative velocity is gradually increasing while the distance between them is decreasing. And at some point, we reach the point of the merger, which is a catastrophic event where it's a chance for people to probe strong gravity and so on. And this is not really, you can't really calculate it without using numerical relativity methods. And finally, there's the part where you can see the whole system is kind of reaching some kind of stability where it becomes just one big black hole. And keep in mind that these signals can look very different for neutron stars and so on, because you can have different things happening in that case, but this is for a black hole. And now to look at this in a different regard, and this is how a theorist is looking at it right now. The same regimes that we looked at, you can look at it in terms of 2 parameters. So one is this log of r over m. R is basically just the size of the system, so the distance between the 2 black holes, and m is the sum of the masses. So the logarithm of this is called the inverse of the compactness. And on the other hand, on the x-axis, we have just the mass ratio and the logarithm of that. So essentially, we see that there's, first of all, one regime that can only be studied with numerical relativity, and that's connected to the merger itself. That's still something where you have to use strong gravity techniques and so on. But what I will be talking more about is what's called post-Newtonian theory. So essentially, you're expanding in 2 different scales. So first of all, you're expanding around flat space, so just around basic Newtonian gravity. And in addition to that, it's also non-relativistic, so you will have expansions in velocity as well. And yeah, to briefly, I'm going to be showing you like where they are in post-Newtonian theory and some other approximations within this. But there are currently some codes. There's a code called EFT of PNG that's published by Michelle Levy at the Niels Bohr Institute. And she has calculated a bunch of useful results that are quite relevant, I think, for the gravitational wave community. And there's also another effective field theory that's used that I'm not talking too much about again, which is called the effective one-body theory. This is something that's been known for a while, and it's quite interesting because they basically can model both the in-spiral as well as the ring-down part of the black hole merger. And you just assume that the black hole is an effective one body instead of being 2. And normally post-Newtonian theory is actually validated against this effective one body formalism. So I would say that's the big formalism behind everything. And the other thing is, why not just use numerical relativity for everything? The reason for that is that if you go back to the previous slide, I mentioned that the in-spiral is actually the longest part of the whole merger. And we know that numerical relativity simulations are extremely time-consuming, and they require a lot of computational power. So they're kind of inherently unsuited to doing this kind of simulation, and it's probably much better treated using analytic methods. So yeah. And I have put in a link here of like an article that actually explains in more detail like the difference between all of these regimes and how they work together and so on. I haven't discussed it beyond this. And I will be talking about now what the formalism that I've been working on is all about. So it's basically just a class of post-Newtonian theory. So we're working at low energies and we're looking at a classical limit where Q over M goes to 0. So that's basically you're saying that the black hole has a very small momentum compared to its very large mass. And you're taking this limit. And this is very interesting because you get a particular class of corrections to these metrics that are, they're called non-analytic contributions, and they essentially describe the long-range effects of having massless particles. So it's telling you like how a photon or a graviton or a massless particle like it can affect space-time at a large distance next to these black holes. And we're going to see now how the analytic computations can actually be used to obtain fundamental quantities. And of these, the most interesting, I would say, are the metric and Newtonian potentials. So these are usually the things that the theorists are trying to calculate to higher and higher precision in order to model all of this. So now the next question is, why is an effective field theory a good formalism to study all of this? And I think it's fair to say that everything is an effective field theory. So that in itself is a reason to treat this in an effective field theory way and use all of the tools that you have at your disposal when you're working with effective field theories. But to put it a bit more like in detail, one thing we know about effective field theories is that they're actually really good at handling a multi-scale problem. So in the case of the previous plots, I mentioned all these various parameters like the mass of the black holes, the physical distance between them, the whether space-time is flat or not, and then of course the whole relativistic thing. And these are all different scales that you have to account for, and there are so many degrees of freedom. And it's the same as in the standard model where you have like a wide range of masses on all of the particles that we have discovered. And we don't know like at what mass a new particle is going to appear. And it turns out that when you have so many scales to deal with, you can systematically deal with them one by one using effective field theory. So that's pretty convenient. And the biggest issue with gravity as a quantum theory or as a theory in particle physics, I would say, is the idea of renormalizability. And I would say effective field theories actually make you look at this renormalizability in a different way. And we know for a fact that it's a very efficient way to actually get numbers out of non-renormalizable theories. And the most famous example of that is Fermi theory and how far that all took us with regards to weak interactions and so on. But in the case of gravity as well, like just going order by order in this expansion allows you to like deal with these divergences in a better way. And it actually makes this whole thing into a theory where you can actually get results. And we're going to see that results, of course. And now in a very schematic, wishy-washy way, I'm going to tell you the general procedure of what to do when you have an effective field theory. So the first thing you have to know is what are the symmetries and what are the degrees of freedom of the theory. And using that, you need to write down a full set of operators, every single one that you can come up with. And that is your non-redundant basis. So yeah, that's your redundant basis. And basically, this can land you up with thousands and thousands of operators, even at a single level. So at this stage, if you want to be able to calculate things a bit easier, it's a good idea to use equations of motion or other methods to relate these operator structures and get rid of the ones that are non-redundant, that are redundant, so that eventually you only get the things that will contribute to your physical scattering amplitude. And since we talked about how EFTs are so important for a multi-scale problem, that's where the step 3 comes in of power counting. So you have to establish what scales you have, and basically the tower of operators that you build has to be based on this power counting in these expansion parameters. And if you do all of this, you'll end up with a reduced effective Lagrangian. And then it's like if you have any quantum field theory, like the standard model, you just sit down and you write down all of the Feynman rules and you're all set to compute an amplitude. So this is kind of what we'll be doing with gravity. I'm going to talk about how this actually works in gravity. Oops. Okay, so like I mentioned, the biggest issue with gravity is the renormalizability problem. And people have known this ever since they looked at the most basic action for gravity, which is the Einstein-Hilbert action. And I'm just going to explain what's in this action quickly, but we're starting with the square root of minus g. its definition is given just right below. It's basically like a determinant of the metric. So it's just a contraction with the regular Minkowski metric. And then you have a Ricci scalar, and you have this factor kappa, which is extremely important because kappa square is proportionate to the gravitational constant itself. So this is the dimensionful constant that is giving us all of the trouble when we want to work with gravity as a particle physics theory. And then I'm going to leave the rest as it is for now and just call it the matter Lagrangian, because it essentially contains all of the matter that you want to include into your theory. And yeah, that's going to be the next step, because our main interest here is to study how gravity interacts with the matter. And by matter, I mean specifically the black holes and the massless particles and so on. So as I mentioned in the procedure before, the first thing you have to do is to, knowing all of these symmetries, you basically write an infinite tower of operators that are consistent with these symmetries. And when it comes to gravity, you can have all kinds of combination of the usual gravitational tensors, like the Ricci tensor and the Riemann tensor and so on. And if you want to work on a quantum effective field theory of gravity, you would have to reduce all of these using equations of motion, and it does get quite succinct. But for the part where we are concerned today, I'm mainly interested in, like I said, how matter interacts with gravity. So I'm going to leave the gravity self-interactions aside for now, because that's less relevant. But now we can get to the power counting itself. So like I said, we're doing a low energy post-Newtonian kind of expansion. So to begin with, I'm expanding this metric that I have around flat space. And this is done in the background field method. So on the first level, you would call it just a Minkowski metric. But when you upgrade it to a background field, you just call it G bar mu nu. And that's just a technicality, but it doesn't change anything for now. And we have this background field, and then we have this other field, which is called H mu nu, which is a quantum field. And that's what we're interested in now. And we see the appearance of the kappa again. And in the following two lines, I haven't explicitly given the factors of kappa, but you can just assume that every time you see one of these H's, there are appropriate orders of kappa associated with it. So you start with just this basic expansion on flat space, but then after this, you end up having to invert this matrix, which becomes a bit non-trivial when you're not working in flat space anymore. And you end up with this whole series, as you can see in equation 4, which is ordered in powers of H, the quantum field. And then the thing that's actually appearing in the Lagrangian, which is this determinant of the metric, you basically use that standard method of writing that the determinant is the exponent of the trace of the log and so on. And you end up with another series that's going on in H. So since we're interested in just the first level of this, we're going to stick to one order in kappa, and I haven't put in any factors of kappa otherwise where they should be. So now we can discuss a bit how the term that we're interested in, which is how this determinant interacts with the matter Lagrangian. And throughout this talk, I'm going to stick to the scalar case because there are some extra technical details if you go to fermions, and I think it's easier to understand if you just look at the scalar case. So we're only considering one order in kappa, and basically we just go back to this expansion from here for square root of minus g. And this allows us to essentially write down Feynman rules as you would in any quantum field theory. And yeah, like we'll constantly be restricting ourselves to one order in kappa, and you'll see a lot of things drop out all of the time because we're interested in only a particular range of corrections in this whole thing. So I've just given you an illustrative example of a Feynman rule that we'll be using a bunch of times in the calculations. But this one is called tau 6 mu nu. And every time you see these two indices, it means that there's one coupling to an energy momentum tensor. So if it's a vertex containing two gravitons, you'll see 4 indices instead and so on. But if you make a naive comparison between equation 6 and 7 and you dodgily derive some Feynman rules, you can see that it looks pretty consistent. And of course, this has been done thoroughly. And yeah, in general, we do have to technically go back to those gravity self-interactions and write down the Feynman rules for all these gravity self-interactions and all the combinations that you can think of with fermions and gravitons and so on. And this has been done. So yeah, basically this procedure can just be extended to spin half particles and spin one particles and so on as you wish. So this allows me to talk a bit more about what these corrections that I've been talking about repeatedly are all about. So as I've written in the first sentence here, these non-analytic corrections that I told you about are due to the effects of massless particles, such as photons or gravitons, at long ranges on the curvature of spacetime. And the reason why it's so specifically massless is because you can look at the expansion of a propagator of a massive particle. So it's just a 1 over q square minus m square. And we take the classical limit we talked about where q over m goes to 0. And you see that it's basically a simple power series. And this is never going to give you any strange functions of any kind. But on the other hand, if you get rid of this mass square and you just have the 1 over q square and you do this similar expansion, you end up with all kinds of strange functions. And the ones we'll see the most are this log of minus q square and the 1 over minus q square, square root of that. And basically, we find out that these correspond exactly to quantum and classical corrections to the metric. So the log terms contribute to quantum corrections and the other ones contribute to the classical corrections. And the only way to know this is to, like normally in particle physics, we take out all the factors of h bar and c and so on. But if you explicitly put in those factors of h bar back into your equation, you'll see that all the log of minus q square terms that show up, they come with a factor of h bar. And I'm going to say why in a second, but we're basically just looking at the Fourier transforms of functions like this. And you can see clearly that they lead to a 1 over r or r square kind of term. And that clearly tells you already that this has some kind of long range implication in, once you go back to position space. And it should be emphasized that this is an effect of massless quantum matter. So you're talking about massless particles like photons. And we're not talking about quantum gravity itself, because that's outside of the regime in question, because that would be strong gravity and so on. So we're talking about how these massless particles affect spacetime around black holes. And the reason I showed you those Fourier transforms is because there's a way to connect the metric and this h mu field that we had to the energy momentum tensor. And this is just by doing a rearrangement of the Einstein field equations, and you get it in the form of equation 13. And there also appears this T, again, it's basically just a determinant, just as the G1 was. So basically this allows you to connect the metric and the energy momentum tensor. And then once you kind of solve this a little bit better to get a better equation between the two, you can use the idea of Green's functions and so on. And basically you end up with the fact that the metric tensor is actually related to some kind of Fourier transform of the energy momentum tensor. And this is why at the end of this, we'll actually be calculating energy momentum tensors and so on. And for that reason, like you can see that when we go back here, when these log and weird non-analytic terms appear in our energy momentum tensor, you know that when we Fourier transform them and go back to the metric itself, we're going to get these long range corrections. So now I'm coming to the transition amplitude itself that we're considering. So we're kind of looking at how two black holes with momenta P2 and P1 and other things to describe their state are interacting with gravity. So I've written both of these equations just to see in equation 15 and 16. And like the idea of obtaining these equations for the energy momentum tensor is simply just a Lorentz decomposition, and then you use the fact that the energy momentum tensor is conserved, and you end up with these expressions. So what we see is a certain kind of momentum dependence, and those momenta are explicitly in 17 and 18. So one is just a momentum transfer and the other is kind of the average of the momentum. So we see some kind of momentum dependence, and in the case of the spin particles, we can basically see this sigma mu nu matrices, which are related to gamma matrices, and thus they're connected to spin. And if you naively just compare the F1 bits, like up to a factor of m here and there because of the U bars and stuff coming in, they basically look quite identical. And it's the same for F2 in the scalar case and F3 in the fermion case. They're also clearly quite intimately related. And this kind of tells you that the spin independent part is contained in these form factors F1 and F2 in the case of scalar particles, of course, and F1 and F3 in the case of the fermion. And all of the spin content is actually in this F2 form factor. And when we do this calculation, we're just going to look at the leading non-analytic terms and just throw everything else out, because this is exactly the limit that we're considering in this case. So just to summarize briefly, we've built up this effective field theory formalism. We have just made a tower of operators. We have found a way to connect, to describe interactions between matter and gravity. And we use this to build these Feynman rules. And eventually, our idea is to come to an expression for this energy momentum tensor and this transition amplitude that is there on equation 15 and 16. And this, when we Fourier transform it, is going to lead us back to the metric itself. So in that sense, we're going to use this entire procedure to reach the metric and find the corrections to it. So now I'm going to show you the basics of the computation itself. So this is just a basic idea of how it happens at tree level. So, I mean, the diagram that you see over here shows actually two photons connected to an energy momentum tensor, but it's just to remind you that the procedure can be used for any kind of particle. But here I'm just showing you the scalar situation even then. So at the tree level, we can basically go back to that equation that we had for the transition amplitude. And we do have some restrictions on the form factors, and we use that to find the other form factor. And we also obtain this particular relation for the tree level energy momentum tensor. At just a single point, it just becomes like a heavy scalar mass. So we're allowed to have this relation. And this is frame of reference dependent. So with these little things, you're basically able to do the procedure that I said many times, where you have an expression for the energy momentum tensor. So now you just Fourier transform it, and you land up with, at least in position space, this is the result that you land up with for the metric tensor itself. So it's all proportional to this minus 2g m by r. And then there's this whole dependence on, depending on the indices and so on. And now if you make a comparison with the Schwarzschild metric that we all know of, it turns out that we're literally getting exactly the same thing. So at least at tree level, the whole thing seems to work. And for fermions, you can do exactly the same calculation. And like I said, the spin dependence only comes into these off-diagonal terms. So the only difference that's going to come is that this G0I component is going to be non-zero. But otherwise, we expect the other two parts to be the same. And that's how it is at the, if you look at the Kerr metric. And I haven't shown the fermion calculations, but if you want, you can look at it in this paper that I will be repeatedly referencing. But it's essentially the same procedure. And this allows us to go to one loop, which is a lot more interesting. And technically, if you're doing this one loop computation, there are a lot of diagrams involved, but lucky for us, we're only interested in these non-analytic terms, and there are only two Feynman diagrams that contribute to that. And I thought I would just show you a basic idea of how I calculated the first one. It's exactly the same for the second one. But the first one is the only diagram that produces both quantum and classical corrections. So I thought it'd be nice to just talk about that a little bit and show the results there. So just looking at the Feynman rules for this particular diagram, you see that we basically have two vertices involving scalars and gravitons. So that's why we have two tau sixes. And then we have the third vertex, which is the nightmare and the reason why no one wants to do these calculations in gravity. It's the 3 graviton vertex. And like I said, because it has 3 gravitons, it comes with 6 indices. And I'm going to shortly show you the expression for it. And the rest of it is just these graviton propagators and then one scalar propagator that comes in the loop. So this doesn't look too bad in itself. This is a pretty standard calculation if you're doing QED or something like that. But now you come to look at what this 3 graviton vertex looks like. I decided to take a screenshot and paste it on the screen because I think it would take me too long to write the whole thing down. But it's basically a very complex structure because all these P's and I's themselves are like more complicated combinations of metrics and so on. So if I wanted to write this on a page or two, I think it would take me easily 10 pages to work out this entire expression, including the vertices and so on. But the good news is that I did manage to calculate all of these things, and I calculated both the diagrams that I showed you for fermions and scalars, and it turned out to be consistent with the paper that my supervisor wrote with his collaborators. And for this, I used a program called Form. And the results that I got for my leading form factor contributions from the non-analytic terms are what I've showed you before. So you explicitly see these non-analytic contributions that I told you about. And then it essentially amounts to the same procedure as before, where you plug this into the expression for the energy momentum tensor, and then you Fourier transform it, and eventually you come back to obtaining corrections for the metric itself. And I've showed you these corrections here. So maybe just in the G00 case, like we start with the tree level contributions, but now we have this higher order in G contributions. So we have these G square contributions, which are the new thing. And you can see that one of them comes with a factor of H bar. And that's mainly been put in there for illustrative purposes than for anything else. But if you do work out the dimensions of everything, you'll see that it needs to have an H bar. So basically, we're getting two kinds of corrections. Like one of them is just proportionate to G square, and the other one is proportionate to G square and this H bar. And these are kind of two separate corrections and two different expansions in that sense. And to definitely know that my calculations are correct, I found out that the G00 and the Gij components were fully consistent between the scalar and fermion calculations, which is what we expect since the spin dependence is only in G0I. And I did find a non-zero G0I for the fermions. And the other way to know that this result is correct is that we do have classical results for both the Schwarzschild and the Kerr black holes, which are exactly these G square terms, but not the ones with H bar. And those have turned out to be consistent. So that gives you more proof that this calculation actually works, however it is.
Sorry, Anagha, can I ask you a question? So what are you comparing with that I didn't get?
This is just corrections to the metric, basically, which you can calculate using, like, if you just work with the Einstein equations in this limit, you're able to get these classical corrections at least. But if you want to go to the quantum corrections, then you have to do something different.
So you're just putting the classical stress tensor corresponding to the scalar field on the right-hand side. So what exactly are you solving? Can you just explain a bit more?
I'm basically just looking at this Feynman diagram, where you're basically saying there are two black holes at the end of this, which are scalar in this case, and you're discussing on a one loop level how it's interacting with this energy momentum tensor.
Okay, but in your calculation, you had to explicitly specify this tau 6, which seemed to be tied in with a specific choice of the scalar Lagrangian. Is it really true that you require that specific scalar Lagrangian? For example, if I added 5 to the 4, what would have happened to your results?
Then you would have to include more interactions and stuff into the theory, but other than that, it shouldn't make a difference, I think.
And this Berenberg original calculation that you're comparing with, which you said that your calculation agrees with theirs. So what did they do? What exactly did they do?
They did the same thing. They did it by hand. They did it using Mathematica and so on. And they just calculated this using Feynman rules, essentially. Because otherwise, if you have to do it through Einstein's theory and work with those Einstein's equations itself, it's a different kind of complicated, I would say. So here they've just used Feynman rules, and yeah, the rest will be about how we can try to find different ways to basically calculate the same thing.
I see. Okay.
Does that make sense, or?
Yes. So they also did essentially the same calculation, but you are doing it in some cleverer way, or so how is it different? So are you just reviewing?
I used a different program. I just independently checked it, I would say.
I see. Okay. Okay. Thank you. Yeah. There's more questions. Ranjan has a question as well. Yeah.
Okay. Yes, I have a question. It's probably a naive question because I'm not very familiar with these things. So you say the results are consistent with the curved black hole. So yeah. So where does the so there should be say the spin parameter coming into the equations, right? Why don't I see it, or am I missing something?
So I just didn't write in the expression here because I didn't want to make it more confusing. But if you look in the paper, they have the full results, and that's consistent with what I got as well. So but you start with some kind of quantum spin kind of stuff, and you end up with this classical spin, those S matrices which are related to the different spin matrices. So you get like a explicit cross product between S and R, and you get some terms that are in the Kerr black hole expression.
So in that case, for example, the G mu nu will have this dependence on this S, right?
Yeah, 100%. But it's only G0I. It's only that one component.
Okay. And does the F?
Yeah. Sorry?
Does the F1 and F2 also depend on this?
No, that was the point. This F1 and F2, like because I'm looking in the scalar case, that's the spin independent part.
Okay, sorry. Yeah.
But for fermions, there's this additional spin dependent part, and that's what's showing up as 0 in equation 28. And if you just look in the paper, or I can show it to you sometime, you do get a non-zero result.
Okay.
In that case. Thanks. Yeah, I just didn't want to complicate it with more notation, so I left it out. Yeah.
So you're thinking about Kerr black hole as a spin half particle here,
exactly.
As a fermion. Okay, but you have to take some kind of semi-classical limit where the spin is large, right? I mean, at some stage, how are you going to do that?
I think that's the part where I do have some confusions about, and that's what the next method is all about, I think, to really understand like this connection between classical and quantum spin.
Okay.
Sorry, can I ask?
Yeah.
Related question. Just I realized when but on to answer the question. So how do you treat extremal black holes?
We don't. I mean, not with this method at least.
Okay.
Like I said, like a lot of it has to be done with numerical relativity, but there are people who are working on some other kinds of expansions on this. But the analytic regime kind of applies mainly to the in-spiral part of the black hole, and that's what it's better at. So yeah, the extreme things, I think it's still something.
No, I'm talking about the extremal black holes where say the spin is 1, A star equal to 1, the reduced spin parameter is equal to 1.
I think people are just dealing with that quite like with standard methods. Like that's what they're doing in these post-Newtonian expansions, to just go to higher and higher spin and just using the same formalism. But I'm not entirely sure what the interpretation of these higher and higher spins is.
Okay. All right.
But yeah, I mean, technically, like you're just saying that this method can be extended to all of that stuff if you can write the right Lagrangian for it and so on. You just need, in this case, you just need a matter Lagrangian and you can see what happens basically. And you could do this with a photon as well, but I'm not really sure what that would really mean for a black hole. So,
okay, thank you.
There is another question from Parthiv.
Yeah.
Yeah, so I just wanted to ask, because I guess you're doing a post-Newtonian expansion here, if I'm not wrong.
Yeah.
That's what you're doing. So this H bar, I mean, what do you mean by this is a quantum correction? Post-Newtonian methodology is essentially a classical thing, right?
So I think that's, first of all, I told you that it's like a particular range of the post-Newtonian corrections where you're looking at what quantum particles are doing at a distance. So it's not exactly the same as the post-Newtonian thing in that sense, because you're just picking up some bits. And yeah, the particles that are, I think like the interpretation of the whole thing is that like even classical objects can have quantum parts to them. And it kind of adds to the whole idea that general relativity is an effective field theory, and there is some kind of quantum characteristic to everything, basically.
So is it like some kind of back reaction of, let's say, graviton or whatever on the metric or the classical metric, something like that?
I mean, I don't think it's actually more complicated than it's going to have some non-negligible effect on the curvature of spacetime. And as you take h bar to 0, that effect kind of disappears as well. So when the photons become more classical, if that makes sense. But I think it's not more than the fact that like photons can affect spacetime at a distance.
Okay, thanks.
Okay, I don't know if there are any more questions because I can't see anybody. So yeah, I have to say that these are all kind of new methods, and I feel like there are a lot of strange things in these calculations and stuff, but there is still a lot of motivation because it seems to work. But I think there's still a long way to go in like understanding what every single detail in this means and so on. And I think the method I'm going to talk about is quite a good example of that, because the whole point of this is that we looked at the 3 graviton vertex and it basically covered an entire slide. But at the end of it, these corrections that we got for the black holes, they were actually quite simple results. And it's clear that most of the 3 graviton vertex is somehow not contributing in the end, and it's not physically relevant, basically, at the end of the day. So is there a way to somehow figure out what's contributing and what's not, and to get rid of the stuff that just complicates your calculation? And a master's student at Niels Bohr Institute had worked on this, that perhaps one can actually find only the classical corrections to the metric by getting rid of all of the quantum stuff, but you replace all of these complicated vertices and interactions, and you basically just replace it with a simple classical source term. And there are ways to somehow make this work for scalar QED examples as well. But basically, you're taking all of these vertices and you're taking this classical limit again, and you're trying to find a source term that you can plug into this Feynman rule expansion, and you get something a lot simpler. And the suggestion that he gave is the one in equation 30, which you can see is much simpler than the old tau 6 that we had, which had all of those momentum dependencies. And the best part about the whole thing is that it actually kills off most of the 3 graviton vertex, because most of the indices just go to 0 and they vanish. So this is a lot, it's definitely a lot easier to calculate. I can do it on a piece of paper in a day compared to the other thing where I definitely had to put into code and so on. But as where we stand right now, oh yeah, and I didn't mention this, which I've written here, but of course, like when we get rid of a lot of these indices in the 3 graviton vertex, we end up with k zeros and k i's, so not the full 4 loop momentum. So we end up with actually simpler triangle integrals that you can solve using residue theorem. And it's a lot easier than actually solving these integrals otherwise. But when I try to reproduce this calculation, I got the G00 results correctly for the Schwarzschild case, but I don't think that it was fully correct. And I think there's some hope that we can extend this whole thing to fermions, because like I said, there's still a lot of, I'm not really sure, and I don't think anyone's really sure exactly how classical and quantum spin go together. And I think that it could give us a lot of understanding. So I think there's a lot of reasons to look into methods like this, which simplify the whole calculation. But of course, you have to make it work. And it is very difficult to just guess something that kind of replaces everything else. So, but yeah, hopefully we can try to find an easier way to do it. But moving on, I'm going to show you just the current state of the art in this. So I got this slide from a talk that was given at GGI by somebody called Mao Zeng, and he's contributed a lot of the results, as you can see. So first of all, it shouldn't be breakthrough. I think it should be, I don't think it should be breathe-through, it should be breakthrough. But we can definitely see that this is a breakthrough after 30 years, because like this has been going on since 1687, as you can see, but it's seen a huge revival ever since this whole LIGO thing has happened, and there's been huge improvements in the precision of these calculations. And I should say what the calculations are first of all, but there are mainly two categories in these expansions. So this kind of encompasses more than what I was talking about. But basically, there's these PN corrections and there are PM corrections. So PN is post-Newtonian, like I said, so you're expanding in this velocity. But PM, on the other hand, kind of has a more explicit, it's harder to calculate, but it's post-Minkowskian. So while you're still expanding around flat space and you can't really reach strong gravity that easily, it's still one step above post-Newtonian, I think. And in the last several years, a lot of people from different communities, so a lot of the names that you see here are people who are well known in amplitudes. But on the other hand, there are also people who work on next to leading order calculations in particle physics for the LHC. And all kinds of people are very interested in just simply making these calculations a lot more precise. And the current state of the art for the post-Newtonian results, I've given a link right at the bottom. I hope you can see it. But they basically have calculated the full fifth post-Newtonian expansion for the Newtonian potential, and they have partial results for the sixth post-Newtonian potential. So this has gotten quite advanced, and it's going to only get more advanced over the years, I think. So just coming quickly to the final part, I don't know how many people know what about amplitudes, so I thought I would just do a very, very brief introduction. But I have just mentioned Lance Dixon's review here, and there are other reviews, including Henrietta Elbang, and there are many good reviews out there. But the whole idea of this amplitudes field is that you're going to change how you look at this problem. And so to begin with, I would say that we should start with this spinor helicity variables and the variables that you use and how you break down this problem. So if you're looking at just a tree level amplitude, like you just imagine, because it's easier that way, you just imagine that you're considering n gluons at tree level and you want to find an amplitude for them, which is a physical quantity. First of all, we know that the color part can be separated from the kinematic part. So all of these TAs and traces of TAs and structure constants and so on, they don't enmesh themselves with the kinematic part of the whole thing. But basically, you can simplify the color part on one hand separately, and you can do the kinematic part as well separately. And what you have here is a dependence on the momenta and the helicities and the color factors. So what you end up with is like a trace of different configurations of those colors that are in the gluons, the color indices of the gluons. And then on the other hand, you have some kind of kinematic amplitude that's, again, dependent on the different kinematic variables and the helicities. So if you just put the color part aside and you say that I've gotten this huge trace of the color component to my amplitude, and you just look at the kinematic part. So I kind of have tried my best. I hope I didn't mess it up. But when I use this fancy eighths for the full amplitude and the regular A is just the kinematic part of the whole thing. And the whole point is to express this kinematic part instead of in the usual momenta and so on, and dealing with the crazy number of momenta you have to deal with. You look at it in terms of Weil spinor products and just Lorentz invariant quantities. And between these two different products that you see, there are all kinds of identities. And this is all given quite well, I think, in Lance Dixon's review. And the warning that I should give everybody is that one of my issues with this field is that nobody talks about their conventions, and as a result, you'll end up with factors of 2 and I and everything falling all over the place. So, but yeah, I hope I've overall been consistent. So using this spinor helicity formalism, like I don't think it gained much traction until this huge development came into the story, which is called the Park-Taylor formula. So I have written down in equation 33 here the Park-Taylor formula as it was given by the authors standing right next to them, so Mangano and Park and Zhu. So this is a formula that describes the kinematic part of the amplitude for n gluons. And of course, this is massless, and this is also tree level. And it's also one particular helicity configuration, which is called the maximally helicity violating configuration. So I think the only thing that should be taken away from this is that if you have n gluons, you can just casually sit there and you have an expression for its amplitude. And this is compared to the whole thing of going through Feynman rules, solving all of these different diagrams, like you have an exponentially growing number of diagrams and so on. But at least for this one helicity configuration, you can get this compact diagram, and it can be extended to other helicities, and a lot of people are working on including masses into this and so on. But it's, I think, the first time we were able to, maybe it's not the first time, but you can calculate something without actually calculating anything, which is quite great if you're dealing with these kinds of things. So the next development in this, I would say tree level stopped being important a long time ago. And it's very important in any field of high energy physics to go to loops so that you can have more precise calculations. And a huge development in that was the BCFW recursion relation. Essentially, it allows you to reduce the loop order, and it's an on-shell recursion relation. And to just put it very simply, all you're saying is that I can like any amplitude is an analytic function, and I can use these on-shell singularities or unitarity cuts in order to reconstruct the expression that I want to. So this actually allows you to express an M-loop amplitude in terms of lower loop amplitudes, and essentially it allows you to extend this Park-Taylor formula to something bigger because it just becomes a building block in a recursion relation in the end. And the reason I gave you all of this introduction was because there's actually an exciting connection between all of this and gravity. So yeah, if you keep in mind the dates of all of this, like this BCFW and stuff came in 2005 as I've written here. But back all the way in 1985, these three people whose name I'm not sure about pronouncing, so I'll just call them KLT. They came up with what are called the KLT relations. This was mainly for string theory at the time. And again, this is one of those things that was kind of ignored until somebody in the amplitudes community kind of picked it up. But to put it very naively, they discovered that actually gravity is just the square of gauge theory. So in this case, I have the full amplitudes, including the color parts. So we know that gravity is supposed to be mediated by a spin 2 particle called the graviton, and gauge theory has spin 1 particles like the gluon. And basically, we found out that all of these color and kinematics can actually just be squared, and you can find a relation between products of linear combinations of the corresponding gluon amplitudes. And I guess you'll also have to note that these gluon amplitudes are color ordered, so you have to be a bit careful there. So like this is, I think, really awesome because it tells you that gravity, it looks really bad, but it's actually not much worse than QCD. And the same skills that you use to solve problems in QCD, all those multi-loop things that we're doing in the LHC, you can use exactly that for gravity if you can exactly find these KLT relations and just relate them. So maybe it's not that impossible to calculate these things, because I think if I had to calculate a crazy problem in gravity and work with like a 5 graviton vertex, I think the 3 graviton vertex was bad enough, basically. So yeah, this is essentially just making the problem so much easier for you. And if you want to read further about this, I also found the BCG relations that are kind of connected to the KLT relations and kind of extend them beyond tree level. I found them quite interesting because it's basically saying that if you look at gravity and gauge theory and you compare the numerators, you can write a certain set of Jacobi identities to like relate them. So that's quite neat, and you can just look it up if you're interested further. But yeah, and this is really the question: would you like to do 2 of these 3 gluon vertices, or would you like 1 of these 3 graviton vertices? which would in reality take pages and pages if you wrote out all of these functions. So I think it's a really exciting development, and yeah, it means that maybe we'll be able to actually calculate these complicated higher order processes in gravity not so long from now. So to quickly conclude, I think I've established that there are these many effective approaches to gravity, and they allow us to calculate fundamental quantities, and they give us these useful results, and we can actually use them to improve our understanding of gravitational waves, which is really great. But as we've seen, like by going just the standard way of using Finemen diagrams and so on, it can get very complicated very fast, because I was looking at a small class of corrections to the metric under certain limits. But if you want a more thorough calculation, then I think new methods are necessary. And I think unitarity-based approaches offer a lot of potential. And I think there's a good chance that this can actually be implemented in a computer, because I don't see anytime soon that gravity will be implemented into MATGraph that easily to higher levels and so on. So I think it's a really exciting time for gravitational wave astronomy for whoever you are nowadays. I think it's exciting to come closer to a more complete theory of gravity and to be able to test gravity in different limits. And I think also just to understand the structure of black holes, if you're just looking to astronomy or if you're looking into the past of the universe, I think there's a lot to look forward to, and there's more and more data coming. I think it's one of the most exciting experiments there is right now. And I hope that they will come to India soon, and I'm sure that it's going to become a really big field here as well as soon as Indigo comes here. So I think that's it. Thanks a lot.
Thanks very much, Anagha, for an interesting talk. Questions? So maybe I can ask you a question. So naively, I would have thought that if you wanted to mimic a black hole with spin, classical spin, which is large, you would consider multi-particle states, as in states and out states, so that in the decomposition there would be some very large spin. So isn't that a correct way of thinking about how to model a large spin black hole?
I'm not really sure if I understood your question.
So the way that you are setting up the calculation from the quantum field theory perspective, you told me that you are modeling a spinning black hole by a single spin half Dirac fermion.
Yeah.
But rather than doing that, wouldn't you try to model it by considering an in state with many particles with small spins, so that in the tensorial decomposition, in the irreducible decomposition of the multi-particle state, you know what I'm saying.
Yeah, I mean, okay, first of all, I think we're trying to look at the black hole in terms of that whole, like a black hole can be entirely described by just those couple of properties, just the mass, spin, and the charge, and so on. So that's the level that we're working on. I think, if I'm right, I feel like such approaches would be more interesting to somebody who's trying to understand the structure of the black hole, because if you think about it, what this formalism is all about, it equally applies to a neutron star or something like that. If you can just find the correct degrees of freedom, because you're just saying that you have a massive point particle with some spin associated with it. So I think that would be more involved, and it would give you more structure of, like, it would tell you more about the actual structure of the black hole, which is not necessarily, I'm not sure how that would fit into the limits of the post-Newtonian regime and so on as well.
Yeah, Anand has a question.
Yeah, I just want to know if you think that if there are some calculations on the gravity side, would that help you in the gauge theory side? Because you said that the gravity result is a square of the gauge theory result, no? So I'm just interested in knowing whether it can go the other way also.
I mean, I suppose
some results?
Technically it can, but that seems like the most difficult way to, that would be like using standard model effective field theory to calculate QED or something, I feel. Like it would just involve so much more.
Yeah.
to calculate something a bit simpler, especially given that we have these amplitude methods like Park-Taylor formula, and it's quite easy to just write an amplitude for QCD.
So now the main obstructions in progress, is it limitation of memory, or is it limitations of algorithms? Because the basic principles, if they are known, all this could be automated, right? So where do you think the stumbling blocks are in progress in this field?
I honestly think it's just a matter of time, because off late you'll see a calculation within this field like at least every few months. So in that sense, it's more advanced than like multi-loop calculations in QCD or something where it takes 3 years to do this. I think it's more like the interest has only started to grow in the last couple of years.
You could drop the screen share now, I
think.
I don't think we need the screen share anymore.
Okay.
Ranjan has a question.
Yes. So I have a question, and it's maybe you showed this, but I lost the connection at the end of your talk.
Okay.
So using these things, can have people been able to, for example, recalculate the gravitational wave, like the spectrum during the inspiral phase? Did you show that? Sorry, maybe I missed it.
I did not show that. I'm not sure if the whole thing has been calculated, because it's still like a thing where now we're at the 5th post-Newtonian expansion, but I think we still need some post-Minkowski stuff, and there's still some way to go in this one, I believe.
So haven't anybody, for example, taken this 5th post-Newtonian expansion, just seen how does the gravitational wave signal look like? I mean, I do understand what you're saying. Obviously, it will not be
I actually don't know about this, and I think I should know about it, and I should look it up. But I've just seen like on the level of like calculating these quantities, like the metric and the potential, but I haven't seen it like reach that experimental stage yet, because whenever I see a plot from LIGO, it usually involves numerical relativity itself.
Yes, correct.
But I'm sure somebody's working on it.
Okay, all right. Thank you for the very nice talk. Thank you.
Any other questions? I don't see any more hands, so let's thank Anagha again for a very interesting talk. Yeah, and thank you very much.
Thanks so much, everyone.
Yeah, bye-bye.
Bye-bye. Thank you very much.